How's everyone doing? Yeah, awesome. All right, cool. We got that working. All right, well, thanks for coming out. It's an honor to be here. Hope you're having a great conference, and a huge shout out to GOTO and all the organizers and so on. So, me and you have multimodal intelligence. And so does Pesto the penguin and Moodang the hippo, for those of you that have been following these guys on social media. How many of you have been following these guys on social media? Okay, so, some of you. I'm just going to set a handy little timer here. And by the way, LLMs are so 2022 and 2023. Now, LMMs, or large multimodal models, are all the rage. And we'll talk about that. So the question is, what is multimodal AI? So anybody want to shout out something? What do we mean by multimodal AI? Anybody? Okay, so video, audio, text, things like that. Yep, that's a good answer. So let's do a quick thought experiment. Okay, how many of you, by show of hands, have ever had a flat tire while you were driving down the road? Quite a few of you. All right. How did you know you had a flat tire? You could shout it out. What told you that you had a flat tire? How did you sense it or detect it or something like that?
Tire was rattling.
Okay, tire starts rattling, yeah. What else?
Car leaning.
Car starts drifting a bit, right? So you feel that, maybe you feel in the steering wheel, maybe even through your eyes, right? You have the lane markers, like the lanes. You see them drifting, so you see them changing, so you're looking at things that are visibly changing as well. Anything else? Yep. Indicator, so maybe you have tire pressure sensors and a little alert comes up, something like that. It tells you that you have a flat tire, something's going wrong, and you had your hand. Yeah, okay, a bad sound explosion. Other things could be there's some sort of vibration or something, right? So we as humans have the ability to perceive things through our senses, right? Whether it's taste, sight, touch, smell, and so on, or even feeling things, right? Just through the seat of our pants, so to speak. So the question becomes, and it's kind of to the point you made, can a machine also do this? Can a machine perceive different modalities of information like we do? And that's what multimodal AI and machine learning is all about. So there's this great paper that came out last year. I'm going to share it as a resource. But basically, the way they define multimodal machine learning in the paper is that multimodal machine learning aims to design computer agents with intelligent capabilities, such as understanding, reasoning, and learning through integrating multiple communicative modalities. The key there is the multiple communicative modalities, things like linguistics, things like acoustics, things like visual things, and physiological as well, like I said, the seat of the pants. And they also go on to define a modality refers to a way in which a natural phenomenon is perceived or expressed. So we're all familiar with microphones. I'm using one right now. And this microphone is able to perceive and capture my speech, my voice, but it could also capture instruments, right, like drums and guitar. Cameras are able to perceive and capture images and video. How many of you have seen Ready Player One, the movie? Okay, everybody pretty much. Yeah, and remember you had those haptic suits, right? They're all in this sort of like, virtual world, and they're wearing the haptic suits, and they're able to perceive through these suits the feelings and the vibrations and all sorts of things through that. So recently, how many of you saw the release, the big news kind of out this week about the release of this multimodal model called Molmo from AI2? Anybody? Oh, okay, so not so many. Okay, so there was an announcement, a big release. Molmo, again, from AI2, it's a family of open, state-of-the-art, multimodal AI models that was just released. And basically, it's, as I said, now everything's kind of going the way of multimodality. So let's take a look at some of the capabilities of Molmo, And again, it's open, so it's not like OpenAI's ChatGPT or Anthropic Claude and things like that are closed source, proprietary. This is open source. So they released some demos that you could check out yourself if you go to the website. So let's look at this one. It says, what kind of music is this? That's the prompt. So basically asking Molmo, this multimodal model, what kind of music is this? And you could see there's a picture. It's basing this question off of a picture of records, right? Now, what's interesting about this is that, and you could see right here, what's interesting about this is this kind of goes beyond your typical, well, first of all, this is something called VQA, or visual question answering. But it goes beyond your typical things you're probably already fairly used to with computer vision, where you have object detection, things like that, okay? There's a cat in the image, and you label it a cat, something like that. In this case, the question isn't asking what are these objects in the image. It's saying what kind of music is this in the image. So, and just as another side note, and a preview into what to expect in the future of AI as we keep going, if this question also asks things like, well, why does this person have vinyl records, and why did they choose this exact kind of music? And the model were to kind of answer through that and come up with different reasons. That's something called VCR, or visual common sense reasoning. But anyway, this is an example of VQA, as I said, kind of an advanced VQA. So basically, to figure this out, the model clearly has to do multiple things beyond just simple detection, right? And you can see the answer here. I'll read it to you because it's probably a little bit small, but it essentially says the collection is primarily alternative and indie rock music. The album covers, so it's doing the detection part that it's records, it's album covers. Showcases a variety of artists, so it knows there's different artists there, and bands. They're typically associated with those genres. And then it even goes on to say what the artists are that it can see, like Panda Bear, Tim Hecker, and Bad Luck, and who are known for experimental and ambient work within the indie and alternative music scenes. So this is interesting because, again, beyond just detecting something in the image, it's also sort of figuring out, which are the bands, what kinds of genres they are, what kind of characteristics of the music it is, and so on. Let's take another look at another example that they give. This one's pretty interesting here. So you have another image, and in this case, it's sort of like, it looks like kind of a weather map, right? And there's even like, it's more of a scientific graph or something of weather. And there's even like a legend and a key thing, and it shows different kinds of precipitation amounts. And the question becomes, describe this image. This is pretty abstract if you think about it, right? Again, it's not just asking like, hey, is there a cloud in the image? Is there a country in the image? Is there a storm in the image? No, this is just very openly just saying, hey, describe this image. And what's super interesting here is that the model, Molmo again, is saying, well, it's a detailed weather map. It's depicting a one-day forecast of precipitation. It goes on to talk about that there's a color gradient scale at the top and ranging from light gray to dark purple. That's indicating precipitation levels and so on. It also mentions a bunch of the countries that are there on the map. So it mentions Cuba and Jamaica and some other ones. And then it says, and this is really interesting because it even ties it to relatively recent, current, actual, real events that happen in the world. It says at the center of the map, there's a black circle with a white dot marking the position of Tropical Storm Helene, which, for those of you that have been following the news, became quite a big hurricane that just ravaged through the US and did all sorts of destruction there. So just with this simple question, or not even a question, right? Describe this image, we get all that out of Molmo. So the question, or the thing we want to understand in order to understand multimodal AI and how it works, is to look at the foundation on which multimodal AI is built. So the terms data and representation are synonymous. And multimodal data is represented in very different sort of ways. So if you hear the term, if you follow much AI or machine learning or read papers or anything like that, you'll see that oftentimes you hear phrases like representation learning, this representation or that representation. So basically, when you hear the term representation, it's basically another way of saying data. But data is represented in different ways. So if we think of, for example, image data can be represented as pixels in a file, like an image file. Under the hood of that file, like a PNG file, is just really pixel data, essentially. But that pixel data can be different color spaces. You could have like images that are in RGB color space, or you could have images that are in CMYK color space for printing. And in that case, there's still files and representations of the same image, let's say, but the representations are different in that the numbers are different because they're encoding different color spaces. So, and when you train models, those models are highly dependent on the representations of the data that you use to train those models. So this is a representation of a course that I teach at Northwestern University, Kellogg School of Management MBAi program in the Chicagoland area. And, well, it's actually a representation of a brainstorming session that I did to kind of figure out, okay, how am I going to improve and sort of adjust the course that I teach earlier this year based on feedback and everything and advancements in AI and everything from the last year. And so I wrote down a bunch of stuff on a whiteboard and kind of thought through all that. And then, as a good person should do when you want to leave the whiteboard for other people to use after you're done, I wiped it with a wet wipe, and then this is what I had on the wet wipe afterwards. So the question is this a representation of the exact same data? Show of hands. Is it a representation of the same data that was on the whiteboard? How many of you think it is? Okay. Decent amount. How many? I'm assuming the rest of you don't. So I would argue that, yes, this is definitely a representation of the exact same data, because it is the data. It's the whiteboard, ink or whatever, right, that now is here. What's interesting is it's distilled down in a way to like this much less complex, much simpler form. And let me ask you another question. What if we could somehow take this more compact, this more sort of reduced version of that data and diffuse it back out into another whiteboard with a lot of brainstorming and ideas of how to improve the class? Well, I just gave you a bit of a preview of not only how some multimodal AI stuff works, but even how things like stable diffusion works and how you get text-to-image generators. We'll talk about that here in a little bit. So going along with this data representations thing, so in addition to what we've already talked about, other types of data representations could be things like scalars, just numbers. It could be vectors, which is a sort of a list of numbers. It could be matrices, which is kind of like a table. You can think of like a table of numbers. Or tensors, like I'm sure many of you have heard of TensorFlow. It's named after tensors. And tensors you can think of as just hyperdimensional matrices. So instead of 2 dimensions, it could be 3, 4, up to nth dimension. It could be infinite in a way. Sequences and so on. And then even like for those of you that have ever coded in R or Python or pandas, data frames. And I knew that cat was going to interrupt my talk. I don't know if you heard the meow there. But so the question then becomes, how do you go from these data representations to multimodal AI? So in order to understand this and sort of build the intuition around how this all works, let's start with natural language. So here you could see there's people talking to each other using what we call natural language. And we'll sort of look at this as a way, again, to develop that intuition, and then we'll move on to more complex multimodal AI. So what is natural language exactly? Well, according to Oxford Dictionary, which you can see if you Google it, it's kind of more formally defined as a language that is developed naturally in use as contrasted with an artificial language or computer code. That makes sense. I mean, it's in the name, right? But the problem with natural language is it's hard. It's way harder than people realize in terms of getting machines to understand natural language. Very hard. And actually, understanding how hard it is really helps get a really deep appreciation for how impressive these models actually are and what they can do. So why is it hard? Well, first of all, words have what's called semantic meaning. So they mean certain things. And they can mean different things, the same word in different sentences. Secondly, you have to deal with context. Like words don't exist in a vacuum. They exist in sentences and paragraphs and papers and reports. The other thing is you have these things called co-references. So in natural language, you might have multiple references to the exact same real-world entity, but it's not using the same word. So how do you resolve that these different words are referring to the same entity? That's something called co-reference resolution. You have things like ambiguity, and where you have a certain word in a sentence that it's not clear what exactly it's referring to, so it's kind of ambiguous, so you need something called word disambiguation. You have parts of speech like nouns, pronouns, adjectives, adverbs, and so on. You have grammar rules like subject-verb agreement, like cat pounces versus cats pounce. And you may have noticed by now that I'm a huge fan of cats. But you also have possessive nouns, things like Alex's cat, which shows ownership of some sort. So let's look at a couple of examples to help illustrate these things. So in this case, we're going to have the same word, but different uses. I work in the garden. In this case, so this is kind of examples of parts of speech. I work in the garden. In this case, the word work is a verb. But I went to work. In this case, the word work is a noun. And it would be awesome if all of us could always go to work this excited as this person here. I'm going to start, like when I get back to Chicago, just start walking down the street on my way to work and like, yeah, I'm on my way to work. Very excited about it. But you could see part of speech tagging there and how that all works. So here's another one. I arrived at the bank after crossing the river. Well, it would appear that the word bank here means the river bank, right? That seems logical. What word in this sentence gives us the indication that the word bank means a river bank? Which word has the biggest impact, do you think? Which one? River. River, right? That helps disambiguate the word bank, which otherwise would be fairly ambiguous, right? But here's a question. Is it necessarily a riverbank? No. What else could it be? Indeed, it could be a financial institution. Would it be wrong to, I mean, there's no way to tell one way or another whether it's right or wrong, right? I mean, you need more context. So this is the importance also of context, because maybe this is one sentence. I arrived at the bank after crossing the river, and I deposited, a couple $100, right? So all sorts of things are complex with language. Here's another one, and this is going to be the same word with totally different meanings. So if someone says, server, can I have the check? In this case, the word check helps disambiguate the word server. But in this case, looks like I have just crashed the server. The word crash helps disambiguate the word server. And in this case, server means two completely different things, right? So how do we deal with all these challenges of natural language? And well, I know in other talks that I've been to during the conference so far, this idea of embeddings has at least kind of come up. I don't know how deep. But there's a thing called embeddings, right? And this was a major step in terms of innovation towards making sense of natural language and so on. So usually embeddings are just a vector of numbers. That's it. And embeddings let's look at this definition from an awesome article there, the Illustrated Word Vec. Learned representation of latent features in latent space, where proximity in space is a measure of semantic or contextual similarity. Semantic for tokens, words, and phrases, and contextual for words, sentences, paragraphs, etc. What does that mean? Well, semantic means the meaning. It just means the meaning. Like, some words have a meaning. Like server in the last example had the meaning of a machine, as long as we knew how it was used in that context, right? But contextual similarity, again, has to do with the context, because, again, language changes completely depending on the context. So let's look at an example more to do with semantic meaning. So these are, again, from the same great article or blog post, but these are embeddings. Let's say we have a model that can convert any natural language, any words, into embeddings, which is just a vector of numbers. Now, on that last definition, if we just go back there for one more second, notice this term latent features. Latent means we don't know what they mean. Humans can't tell what they mean, but they're learned by these models. So essentially, you pass language through these embedding models that create these vectors of numbers, and somehow these numbers represent something about the words or the sentence. even though we don't know directly what those things are. That's what makes it latent. And the best way to think of it in the next case is think of like baking a cake, right? When you bake a cake, you have a recipe, and that recipe probably has eggs, it has yeast, it has flour, different things. So the recipe makes up the cake. Well, turns out that words have latent features, which are ingredients of the recipe of a word that give it the semantic meaning that that word has. And we can represent those as just vectors and numbers. And again, we don't know what those numbers mean necessarily, but if we look at them more like a heat map, just to where the color sort of represents the sort of the value magnitude, if you will, of each number in the vector, we could see that for these words, some of them have quite a bit of similarity in certain positions of those latent features, and certain ones don't. They're not so similar. But we could certainly see there's this one like vertical red line. So in that particular latent feature in this recipe of all these words in embedding space, there seems to be this really strong commonality between all these words. What might that commonality be? If you had to guess, again, it's latent features. We don't know. The machine learned it, learned some features, recipe ingredients. But if we had to guess, what might it be? Noun. What? Noun. Noun? Okay, yep, could be noun. What? Language, I think you said? Could be? Human, yes. I mean, that would be my guess. But again, we can't tell because it's latent features, right? It's a machine just learns these things and it runs with it, and it makes LLMs and everything else possible. But yeah, that's probably a pretty good one because they are sort of all having to do with it. There's probably other features in here which might capture semantic concepts like royalty, let's say, because some of them are to do with that. Some might have some concept of female versus male, like more of a sex type of feature and so on. But what about that context? So semantic meaning is key, as I mentioned, although, again, context is also super key. So for machines to exhibit human-level intelligence, they definitely need to understand context too. And by far, sort of the biggest, most groundbreaking breakthrough innovation that's allowed us to figure out all these things for, again, we're working with natural language to start, has been self-supervised learning. In this case, it's almost like you take unsupervised learning, which means you have all this data, but you don't have it annotated. There's no labels or anything. And you turn it into a supervised learning problem by labeling it with itself. And here's Yann LeCun, very famous, AI, godfather of AI, all that sort of thing, created this awesome slide here to help illustrate this. But essentially, think of like, let's say you have all of Wikipedia, for example. And you want to do self-supervised learning on Wikipedia so that you could create a model of language, like what we call a large language model, for example. Well, because you have all that language, some of the words in Wikipedia could be the supervised labels of some of the other words without actually having to hand annotate anything. So in this case, you could do it different ways. One could be you predict the future from the past, meaning you sort of mask the words to the right in sentences, let's say, and use the ones before to kind of train on the labels of the words in the right so that once you've trained it, you could take away the words on the right, mask them, and then use that model to kind of predict those things. And so on. And you could do it from masking words on the left and words in the middle and up and down and all sorts of stuff. And of course, this all led to this famous transformer model. I believe in the opening keynote of the whole conference, we heard about this extraordinarily famous paper called Attention is All You Need, where this was kind of introduced. And essentially here you have an encoder side on the left and the decoder side on the right. And then when you combine both the encoder and the decoder, you have what's called an encoder-decoder, or the full transformer architecture. And this thing is what makes large language models and large multimodal models possible using self-supervised learning. One thing to note, by the way, is that you don't need both sides. They're actually trained independently, and you can use them for different things. So encoders, if you just use the left side, that's where you get models like BERT, if you've ever heard of BERT. On the right side, those are GPT models. So when you use ChatGPT, OpenAI, Claude, Anthropic from Anthropic, or Gemini from Google, any GPT model whatsoever, you're actually using only the right side of a transformer. You're not using the whole transformer. And to help with all those complexities of natural language that I mentioned before, you have these things called attention mechanisms, both self-attention and multi-headed attention. I won't get into all the details of how they work and everything, but needless to say, they allow you to learn how to do the word disambiguation, how to deal with grammar rules, how to deal with co-reference resolution, how to deal with semantic meaning, how to deal with contextual meaning and changes, and so on. So this is also another breakthrough that's allowed us to get to this point of seeing and using the models that we see today. And you can even visualize this idea of attention. Not only does it help do all those things and solve all those sort of natural language problems that are very difficult, it goes back to when we looked at that example of I crossed the river, the bank, I went to the bank by crossing the river or whatever, and we said, well, the word river had the biggest impact to help disambiguate the word bank, right? That was essentially demonstrating this concept of attention. And not every word in a sentence or in a given context has the same influence on those kind of other words in the context. And so here is a way that once you learn these attention through these attention mechanisms, you create something called attention scores, and you could visualize them kind of like a heat map to see in any given sentence which of those words are creating more of an impact or influence in solving those challenges of co-reference resolution and so on. And with the left side, that encoder side, remember we saw the queen and the king and the everything else? Those were just semantic word embeddings, but we need highly rich, deep, contextual word embeddings. And to get that, the transformer also helps with that. Because again, on the encoder side, the left side, models like BERT, now we can pass in, instead of just one word and figure out what the embedding for one word is, we can pass in entire sentences or entire paragraphs, and we can get out also an embedding, a vector of numbers with latent features, but in that vector, it contains all sorts of contextual understanding. So does all of this apply only to text? Because again, we've just been talking about natural language. And the answer is absolutely not. Data representing any modality contains both semantic and contextual information that can be learned and handled, and modeled. So for example, how many of you saw the Silicon Valley hot dog, not hot dog episode? Yeah, okay, cool. Super funny. If you haven't seen it, check it out. But essentially, even images, right? In a cat, instead of the elements of an image being things like tokens or letters or characters or words like in natural language, in this case, we have pixels or groups of pixels. So the semantic meaning of a given pixel in an image, let's say, might be eye. Maybe it's a pixel in the eye, so it has sort of this meaning of what it means to be an eye. But it has contextual meaning as well, because there's certain pixels that are in the whiskers, for example, and as far as context of what it means to be a whisker in the face of a cat, it means you're probably coming out of the nose, you're near the nose, you're under the eye, and so on. So just like words have both semantic and contextual meaning in language, so do pixels in images. And the same is true for audio and video. So everything we've discussed so far helps with unimodal AI, like LLMs up until recently. But what about the multimodal models like we see here, right? Midjourney for text to images, and then you have Claude and Gemini and so on. So let's take a look at the inner workings of how this all works. Now we're going to talk more about the multimodal side. So again, it starts with representations. But now, if you look here, you have two different kinds in this particular case, right? On the left, it's joint representation. On the right, it's coordinated representations. So the different colors are different modalities. So on the left, maybe that blue is natural language data, text data, and the orange is pixel data from images, let's say. On the left, when it's joint representation, you might encode that information through an encoder, and then you create a single embedding, a single representation, a new representation that encodes both the data from both modalities, so the text data and the image data in the single representation. In the other case, you have coordinated representation, so you keep the modalities separate. So you still have text data, you still have image data, you run them through encoders to get that rich semantic and contextual embeddings that machines can model and understand in ways that we can use to do pretty cool stuff. But they have to be coordinated somehow, and we'll see what that means here right now. So in order to coordinate stuff, you have to first find the best representations for the different modalities of data like we just talked about, but you also have to be able to model those connections between the different modalities and figure out sort of how are they related. So in this case, you could see there's two main categories, like statistical relations between modalities and then semantic relations between modalities. So in the statistical side, you might have things like correlation. For example, ice cream sales is correlated heavily with summer, like hot months, right? People buy a lot of ice cream and eat a lot of ice cream. But you might also have causal relationships, cause and effect. So if I go to the bar when it opens later and I drink too much tonight, which you never know, I'm going to probably have a headache tomorrow because of that causal nature. So that's some sort of relationship. Now, in that case, there's different modalities. So the red triangle might be, again, images, and the blue circles might be audio, let's say. So it's looking at different modalities and how they're related. In this side, semantically, the same meaning. So going with the cat example, let's say we have an image of a cat as the red triangle, and we have audio of a cat meowing, right? They're semantically they represent a cat, even though one's sort of an audio representation of a cat, the other one's an image representation of a cat. We could also have a text representation of a cat, which is literally the word cat, right? So in that case, they have semantic relationships to each other. And then the other one, you could have something like more of a functional relationship. So here's an example of image search using multimodalities, but keeping the modalities, the representations of the modalities separate, but putting them into what's called a joint embedding space, meaning different modalities are projected into the same sort of theoretical sort of numeric space, for those of you that ever took like linear algebra or vector calculus. If not, don't worry about it. But you put it in the same space, and essentially you can then ask a question like, hey, get me a painting of a mountain landscape at sunset, is the example here. Well, the query is the blue, so that's natural language, it's text. But because we have a joint embedding space, all the images are also in the same space. So there's this concept of nearness to each other. So if any of the images fall within a certain distance in this joint embedding space of the query of the natural language, then let's just pull out all those images. And now we've done a multimodal AI thing because we use text to extract or retrieve or search for lots of images. Another example, and this is zero-shot image classification. Classification is where you assign a category or a label to something, right? So in this case, we might ask for, hey, what's the class of a painting? And then we get back that the class is illustration. Or what's the class of handwritten text? And we get back that the class is text. And the reason is because, again, we have this joint embedding space where we have images, but we also have classes that are sort of encoded into this space. And speaking of generative, so in generative AI, right, that's kind of all the rage right now. Everybody's talking about generative AI. It's not just LLMs, it's not just LMMs, it's generative AI. So what does that even mean? And how is that related to multimodal generative AI? Because even just the text LLMs is generative AI. You put in text, you get out text, right? Hey, write me an email to a client that I'm going to be late to the meeting this Thursday, and you get out the email. That's generative AI. You generate an email from a prompt. But there's other kinds of generative AI, including the multimodal stuff that we're talking about today. And generally speaking, there's three kind of categories there. There's summarization, translation, and creation. So again, the different symbols represent different modalities. So the circles could be text, and the triangles could be images, let's say. So maybe you have lots of text, lots of images, and you want to summarize down to a much more distilled version of that stuff. So not as much of the data, more of a compact information, kind of like my whiteboard example earlier. Or maybe you want to translate from one modality to the other. So you see the circle to the triangle. That would be a perfect example of text to images, like Midjourney or ChatGPT does that now, or text to video, like Sora. And then you have creation, where you could create modalities, actually not from other modalities directly, but from embeddings, from these joint embeddings or any sort of embedding that captures semantic and contextual meaning in numbers, in vectors of numbers. So for example, we have text to images, where a lot of these images in my presentation today are generated using ChatGPT. And in this case, the way it works is very cool. This was part of the paper that OpenAI released on DALL-E 2, explaining how this works. And these models are still heavily used today, the underlying models. But essentially, you have a model called Clip, and you have a model called Glide. In this case, you have a caption. Let's say you have lots of images with captions. So, just describing the image. In this case, maybe you have a corgi playing a trumpet as an image, and then you have the caption is a corgi playing a flame-throwing trumpet. Well, we can pass that caption through a text encoder and get out an embedding that contains the semantic and contextual meaning of that caption. We could do the same with the image, pass it now through a vision encoder, an image encoder, and get out of there an embedding of the semantic and contextual information from the image. And then we could create a model, like sort of train something that learns relationships between text embeddings and image embeddings. Okay, just that's it. So it goes back to those connections and associations we talked about before. Once we have this sort of pre-trained model from Clip, then what we could do is we can take that caption, or any caption for that matter, and we can now encode that caption again to get that embedding. But then we can diffuse it through this other sort of, I won't get into the details there, but it's sort of a decoder. This is kind of how stable diffusion works as well, by the way. We could diffuse it because we know the relationships between text embeddings and image embeddings, we can then get out an image embedding that has similar semantic and contextual meaning. It may not be exact, but it has similar, and then create an image from that. That's what diffusion's all about. That's also why, by the way, text-to-image generators, when you use them, if you keep hitting refresh or keep doing it for the same caption or same prompt, you'll get different images out every time, because it's diffusing from more just the underlying latent features that we talked about earlier. So as long as it has the core semantic meaning and contextual stuff in the final output, then it did its job. But there's no guarantee it's going to be the exact same final output, because it's generating it from just a much smaller space of latent features. So what about tomorrow? Where are we going? Now that hopefully we all have a better idea of kind of how this all works, what LLMs and LMMs are all about, how the representations work, the different modalities, how you go from different kinds of modalities to others. Obviously, it's more complex than we talked about today, but there's lots of great resources and papers that you should check out if you want to learn more. But what about tomorrow? So I'm going to just show you a quick video. Okay, so you get the point. I'm going to stop that. So, by the way, I chose that video mainly because it has a really awesome soundtrack, or like a song in the background. How many of you have ever used that software, by the way, Toggle Track? Okay, some of you. Yeah, it's a cool software. I didn't play it to promote it, but the point is what if I could go to an LMM, right? And it's not just two modalities, but it's all sorts of modalities. And I can say, hey, create an explainer video for my brand new, super cool, high-tech product startup. And I want it to have this kind of music in the background and these kind of characters and be really funny and like blah, blah, blah. And then out you get the script. You get a video complete with the script, complete with characters, complete with animations, not so dissimilar to what you just saw right there, right? All in one go, in one prompt, in like, let's say 30 seconds or less. That'd be pretty impressive, right? Well, we're definitely already kind of there, and we'll definitely be seeing more of that. And hopefully now when you start to see more of that, you'll understand more about how it all works under the hood. And with that, please rate this session, and thank you very much.